Hello, friends. Now we're going to talk about double integrals in polar form. So we're going to do a little quick review to remind you what you should know from trig about polar equations. So one thing we want to think about, when we start talking about polar equations and defining all of our rules, we think about the unit circle. And the unit circle in rectangular form would be x squared plus y squared equals 1. So these are rectangular or a rectangular equation representing this unit circle. So when we start to consider this as like a bounded region and trying to find bounds in polar form, we might rethink this and say x squared plus y squared less than or equal to 1. That's giving me the inside of this circle. Well, if I wanted to define that region using polar, we talk about polar in terms of r and theta. In this situation, this represents all circles with a radius between 0 and 1. And the angle measures are between 0 and 2 pi. All right, so that should kind of make sense to us. Also, we can think about this. So let me give you a different example. Maybe we have a region that is defined to look something like this. So we've got this space in between these two arcs representing our region. And I'll define that as 1 and 2. So if we wanted to define this using polar coordinates, in this situation, that radius would be between, say, 1 and 2. And my angle measure theta, that would be going from 0 to not 2 pi, as I started to write. We go from 0 to pi. Okay, so that's the kind of logic we're going to be using when we're setting up or determining our bounds. We're always thinking about that angle as a counterclockwise rotation off the positive x-axis when we're defining theta. And then the radius is, an extension out from the origin. So we're always moving out from the origin in the direction of that provided angle. And we've got some common conversion formulas that we use to help us convert. We have r squared equals x squared plus y squared. And we also say that x is equal to r cosine theta. And we say that y equals r sine theta. We could also say that tangent theta is y over x. Okay, so these are some properties converting between rectangular and polar coordinates that we should be familiar with. If you need some review, send me a message. I can send you something else that might help you to look back on. So now that we've had that refresher, let's think about how we're going to integrate across some region for a function in polar coordinates. So we're going to take this expression, and the derivation of it is in your text. I'm not going to derive this here, but essentially we get this extra factor when we convert, and we convert these bounds and this region all into polar coordinates. We're going to define this and we'll say, well, we have some theta from an alpha measure to a beta measure. And then we have some r sub 1 is a function g sub 1 of theta. R sub 2 is equal to a function g sub 2 of theta. And then we think about that function from r theta. So the way we have our bounds is we're always going to have, and this is extra, we have this extra factor, r dr d theta. Okay, so this r is going to show up. The derivation of why it's there is in the book. I'm just going to tell you it's there and say hey, remember to put the R in there. So we'll integrate with respect to R first, and these two R's, my radii, will be these bounding theta functions. And then our theta, that would be in radians, maybe from 0 to 2 pi. So first we integrate with respect to R, and then with respect to theta, and it's always that way. All right, so the main thing you want to take away from this is you must include this additional extra factor R. So if we are trying to integrate something in polar, we're first going to sketch our region R, and we're going to define and label those bounding curves just like we always do. The second thing that we will do will be to find our R, our radius limits of integration. So what we're going to do is we're going to draw some ray L out from the origin. I'm going to draw a picture here in a second, but we'll draw some ray, and it's going to enter our region, and then it will exit our region. So that's going to give me my upper and lower bounds. Where you enter is your lower bound, where you exit will be your upper bound. And then the last thing we'll do will be to find those theta limits of integration, which is a positive rotation off the x-axis. So I'm going to think about this in both dimensions. I'm going to think about my region, R. So if we think about that, in our xy plane, maybe we have some region that has some measurement, we'll say here, alpha, and then some second measurement, beta. So those are my theta values. I would have theta equals alpha and theta equals beta. And then maybe they're bounded by these two curves. So extending out, that first curve, that would be my R sub 1. That's a function in terms of theta. And then my second curve that I would reach would be an R sub 2. So we extend out, we enter, and then going through here, this would be the second curve we reach where we exit. All right, so just keeping in mind R sub 1 is some G function of theta, and R sub 2 is also a function of theta. So we have these curved regions. So if this was our region right here between these two rotations and then extending out. And so what we're looking at when we think about evaluating this, we think about that in 3 space. I've got my X, my Y, and my Z. So that same angle, we rotate out positively off the x-axis towards y. So there's my theta equals alpha, continuing around. Maybe I would have some theta equal to beta. My region is bounded by these two functions here. So this is my region R. And we're looking at mapping that up to some surface, right? Where does that imprint on that surface in space? And we're finding the volume of the region between that base area and that height, the surface in space. Of course, that inner radius, that's my R sub 1. My outer radius, that is my R sub 2. So let's look at an example. So for this example, we want to find the volume or integrate twice sine theta across some area region. So R is the region outside the circle, R equals 2, and inside the cardioid, 2 plus 2 cosine theta. And we're defining this only in quadrant 1. So what we need to do first is to find our region, our limits of integration, which we'll draw a picture, and then we'll evaluate it. r equals 2 is a circle of radius 2, which looks roughly like this. And the cardioid, r equals 2 plus 2 cosine theta. And you can graph that on your TI-84, put it into polar mode, and that converts your variables into r and theta. So, but what that cardioid looks like is roughly like this. So it's called a cardioid because it's a kind of a heart shape. So we are looking at the region here only in quadrant 1, outside the circle and inside that cardioid. So how do I set up my bounds for integration? Now, theta always goes on the outside. And if we look at graphing this from here up to the vertical y-axis, that's going to be theta equals 0 to theta equals pi over 2. My second bounds of integration. So when we look at doing this, we're going to go from the center out. The first thing we reach is r equals 2. The second function we would reach would be r equals 2 plus 2 cosine theta. So those are my bounds. My function was given. That is sine theta. And so when we are setting this up, whenever we're working in polar coordinates, we have to remember we need to write that extra factor. So I've got this extra r and then dr d theta. So this is my setup to evaluate this integral in polar coordinates. Pause, make sure this makes sense to you. So the setup is what we're really focused on here, making sure we understand how to set it up because the integration shouldn't be too difficult for us at this point. I'm going to work through this. So we've got 0 to pi over 2. Of course, those are theta bounds. And if we integrate sine theta r dr, so we're integrating with respect to r, that means sine theta is a constant, and we're going to get 1/2 r squared. So I have here 1/2 r squared times sine theta. R equals 2 plus 2 cosine theta, and r equals 2 d theta. Now we have our busy work algebra where we plug 2 plus 2 cosine theta into r squared, square it, and FOIL and distribute, and then we plug a 2 in. And so what we get looks like this. I took that 1/2 and pulled it out into the front. We have to FOIL, distribute, and then I've got 4 sine theta. Some foiling looks like this. When I distribute that sine theta to all 3 of these terms, I'll have 4 sine theta minus 4 sine theta. So my next step is 1/2, the integral from pi over 2 to 0, or sorry, 0 to pi over 2. We've got 8 cosine theta sine theta plus 4 sine theta cosine squared theta because that first and last term canceled. So I'm going to do 2 things. I'm going to factor this 4 out. That will turn that into a 2. Factoring a 4 out, I'll have a 2 in front. And then each of these can quickly be evaluated using a U substitution. So now I have separated, I factored out my 4, I separated each of these so I can perform my U substitution. For the first one, I'll say U is equal to sine theta, and of course that means du, the derivative of sine, is cosine theta d theta. Looking at changing my bounds, if I do u equals sine of 0, I get 0, and u equals sine of pi over 2 gives me 1. So I have 2. That 2 is in front of everything because this 2 will factor out, and I will have u du, and my bounds will go from 0 to 1. So we'll say 0 to 1 u du. And my other integral, I will let u equal cosine theta. So u equals cosine theta. That means du is negative sine theta d theta. Changing my bounds, u equals cosine of 0 is 1, and u equals cosine of pi over 2 is 0. So that would be 1 to 0. And those are in the reverse order, so I can flip them and make this negative. But I'm also going to put that other negative in there, which would make that positive again. So just reiterating, I'm going to flip these bounds, which negates it, which would make this negative. But then when I do my u substitution, I'm going to have that extra negative, so it will stay positive. So I'm going to have u squared sine theta d theta. That was my negative du. So I've got u squared du. And now we just need to integrate each of these. So I've got the 2. I'm going to integrate u, that is u squared. Because it's the 2 in front, we'd have 1/2 u squared. So we just have u squared from 1 to 0 plus u cubed over 3, also from 1 to 0. Plugging in 0 in each of these situations is going to zero them out. So I've got 1 plus 1/3. 2, I've got 1 plus 1/3. Of course, subtracting 0 wouldn't matter, so that's 2 times 4/3, or 8/3. And that concludes this video. That is how we take something and evaluate a double integral in polar coordinates. Main takeaway is as we think about this, we just really want to remember that we've got that extra variable that we have to throw in there, this extra element. It's very important. If you forget it, you won't get the correct answer. As always, email me if you have any questions.